Hey, good morning, everyone. I can start, right? Yeah. Good morning, everyone. I'm waiting for your questions. Meanwhile, um, I'll just give you an overview of what the course was and hope you are following it up. Um, the course was on the course was mainly to cover different control aspects, mainly which controller it when we are exposed to different kinds of controllers, which kind of category of the control should be applied in what scenarios. At the same time, we only focused on PID control and various different system models. Where will we be able to apply the PID and what kind of control objectives um, will be able to satisfy? We know PID is a simplified structure. At the same time, it has a physical meaning. At the same time, implementation wise, it is easy. So it becomes more or less easier to implement the control, tune the control parameters. So we also looked into tuning the control parameters, different ways by which your PID structures can be connected, simplify the model such that you are able to apply the PID control. But yes, we already know that not all kinds of control objectives can be satisfied with the PID control. But we know what can be satisfied. So that's where the trick is always. Right? Let me know if you have any queries related to any lecture slide. I have my lecture slides are also being uh, be with me. So you have any difficulty, please shoot out the questions. Okay, so let me bring in some. There are no queries coming up in chat, or maybe perhaps somebody is typing or whatnot. Bharti ma'am can help me with that. But at the same time, I would encourage you to now see any system in the okay, these are technical difficulties. Bharti ma'am can take it. Lecture 6 material is not available. Uh, we'll take a look at it. Lecture 6 of which week? Week 1, week 2? Navendu, could you please tell us? It will help us more. Yeah. So I was speaking about looking at any system as the all right, control system, whether it's an open loop system or or a closed loop system. I gave an example of eyes, and I usually give an example of eyes or touching hands on the hot plate or whatnot. So your brain gets signals on whether it's a hot plate. So then you try to move out, or you hold it using a handle or using some other material or whatnot. But that's the control system that is working, right? So right now it's an open. Is it a closed loop and open loop system? It's a closed loop system because based on the feedback, your action happened to move your hand away. All right. So this way, every system, each and every action, you will be able to relate in terms of the closed loop system. What is the feedback received? What kind of measurements were received? You would be able to understand this. All right. So the queries are now coming. We have Sudarshan asking, what is the advantage of series PID from over standard form? It's the implementation point of view. Or if you see, the series PID has proportional, integral, and derivative terms coming up. It's if you see the derivative control and the derivative control implementation. I spoke about that. Derivative control from the implementation perspective is always harder for the same, especially if you are doing it using the computing systems. You need to convert this derivative into difference equation, and then difference equation signals are pretty noisy, and any noise into these signals, and you take the difference of that noise, it turns out to be um, pretty noisy outcome. I'll give an example using, let me just present my screen. Yeah. Okay. So here what I will try writing is, if I have a time series, time on the x-axis, and there is some signal x of t over here, right? In our case, it's usually the error signal that we are talking about, right? So we take the we take the derivative of dy dt of e of t. All right. Okay. So now this error signal is gradually decreasing or going up and down. Now, if, yeah, okay. All right. Thank you. Right. So now if I'm taking the differentiation at certain points, this is not writing. Okay. Something went wrong. I have this signal which I drew as E of t. Why is this not writing? Okay, when this is E of t and this is time. Now when I'm taking the difference, right? Difference at different sample time instances, say big T and 2t time instance. So this difference is going to be, if the signal is this kind of very nice wavy signal, that's fine. But typically the measurements are corrupted with high frequency noise. And this high frequency noise gives you trouble always when you do the differentiation. So this series outcome I have mentioned um, in the notes, saying that in the lectures, saying that this difference or the derivative needs to be always associated with low pass filter. Now, low pass filter appearing it in series or in parallel makes a difference. So just go back and see and analyze it based on that. The reason is the derivative, which is always notorious, right? Okay. Let me now go back to my thing. Okay, now Navindu's question. Navindu's asking, what is actual use of PD control? The PD control, proportional and derivative control, is used whenever there is a derivative. It's basically a good idea to take care of. The derivative is like you are taking care of the future steps. So you are more or less looking like as a prediction of the error being done. So that is helpful in the cases of the faster dynamical systems. Okay. At the same time, the PD control has a beautiful characteristics of giving you the stability, giving you a larger stability margins. If I may again go back to my slides and draw something over there, I will help you understand how is it increasing the stability of the system. So, okay, I am in this screen. Um, Here, if you look at the Nyquist plot, Nyquist plot of a first order system, for example. So Nyquist plot is based on the frequency. It's a frequency plot for getting the stability margins and so on. So here, the typical plot is like this, and this plot should not encircle -1 0 point, if you recall that. All right. So what happens if my frequency is, say, frequency of operation is this? All right, this point on the Nyquist plot is my frequency of operation. So I have this much available stability margin in order to cross this -1 0 point. So what is the stability margin helping? This will allow my proportional gains to be this much, right? Not exactly this magnitude, which we can always map it to. So my proportional gains can become this much. Now, with the derivative control in the loop, we are adding the phase lead. So, phase lead will allow my Nyquist plot to go in this direction. So, it will move away from -1 0. And as soon as it is moving away from -1 0, it is increasing the stability margin. So, you will be able to have extra proportional gain with the derivative added. And that's where the actual use of PD control do come in. Right? Okay, Shivam. Um, Thank you so much for you found this particular lecture series interesting. Your question is why we call it intelligent feedback control. Will intelligent links with some kind of adaptive control or AI based? Exactly. In order to consider this as intelligent control, we'll have to consider automatic tuning of the system, all right, to a certain extent. Now, automatic tuning, this auto tuning factor can be considered as with the help of the step test being done, identifying the model again, and then automatically adjusting the tuning of the control parameters, which is done in the process industries, by the way, right? But in order to do that, one has to consider either shutting down the plant, which is not a good idea. So, can I do it online? And repeatedly whether I should apply auto tuning at certain intervals or it is taken care in case of the data driven methods. Anything that gets changed, it is automatically taken care and whatnot. So that becomes the intelligence part of it, right? To certain extent, that's what is being covered in the last week of the lectures. All right. Yeah, week 1, lecture 6, we will take care of it. One can look forward for adaptive ways also. Adaptive part is mainly to consider the nonlinearity of the system to be considered, right? So not when the system is pretty nonlinear, and then or the environmental factors are changing drastically, such that your system transfer function is changing. So then your adaptability kind of things to come in. So intelligence is what more towards considering my control structure as fixed, which we fixed as PID. All right. Now, structure is fixed, but changing the gains, KP, KI, and KD, based on the system changes, based on the changes in the system or the environmental conditions or the disturbance characteristics coming from the environment as right. And it should do it automatically without manual intervention. uh, that should be the aim. And then you should call it intelligent system, intelligent control. Yeah. 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 Um, can I re-explain the model deduction procedure? All right. Can you point out, Navendu, it will help me which week and which lecture you are referring to? That will be easier for me to pull out the lecture here. Week one, which lecture? Lecture three. Okay. All right. So I have my slides with me and let me share with you. Um, yeah, all right. So here is what my like model deduction part is, and we know that we are applying it based on the if I have a very high order system, many number of poles, we want to consider it to be of reducing it to first order or second order system. And which one to consider first order or second order comes from the step test. You apply a step input, see the response of it, you will be able to judge whether it's exponentially increasing and reaching it to the steady state, or is it oscillating and reaching to the steady state. If it is oscillating, it is second order system. If it's reaching asymptotically or to the steady state, then you can nicely approximate it as a first order system. At the same time, we'll have to consider approximation based on the frequency of operation. All right. So if I have this kind of, if I consider my highest frequency of operation as omega star in this case. Okay. So what we'll consider for PI controller, for example, I'll consider omega star. This example gave you omega star is equal to omega 145. All right. So what we will consider, this particular frequency corresponding to a time constant, we will consider breaking down the system in terms of low frequency and the high frequency part. Low frequency part we'll consider as is. For the high frequency part, we'll consider the getting the average resident time for the high frequency part. For example, this is what my system G of S is, and we have this particular average resident time given by T3 plus T4 plus T5 minus, of course, there's a time delay, and that's the reason plus L coming up, and then numerator time constants, right? Or the time constants corresponding to the zeros of the system. So now this stochastic half rule, you have many different ways to reduce it. I find this particular rule very straightforward to explain, so I brought it up. In order to do that, so what we'll consider is in this half rule, if it's a first order system, we'll find out what is the average resident time for the high frequency part, and then do this kind of a application into this particular formula in order to consider what is my first order system comes in and so on. So you can see that the breakup that we are doing it as 1 by 1 plus STS. So this TS time constant comes up there, and then high frequency part turns out to be calculating what is my average residence time corresponding to high frequency. We'll not play around with the delay. delay term turns out to be L directly over here. So this gives you the high frequency component effect on the delay being calculated like this, and pole, uh, the time constant corresponding to pole turns out to be T plus Ts by 2. So T is your this that is to be calculated later on, right? T1, T2, and so on. Okay, so I think the example was given here. Now, um, yeah, I'll just quickly cover this example once again. This is omega 90 is 3 for this particular example, omega 180 is 31.6. So then you can consider, for example, my omega star where I want to break this, but my frequency of operation is omega star is going to 3. So what is 3? 1 by 3 is point, you consider 2 pi by 2 pi f. 2 pi by t is equal to omega. So the where I want to consider breaking down is 1 by 1 plus zero point 0.1 s. So my GL of S is only the low frequency part, which is 1 by S, whereas high frequency term turns out to be this. So my TS is now zero point 0.1, and then we'll calculate based on what my GL part is and what my GH part is. And then GH part turns out to be giving you this particular average residence time, which we substitute directly into the stochastic rule, and we get it. I hope the entire um, jugglery over here is to get what is my average resident time for the higher order term and what is the low frequency term, and plug in into the formula. It's a formula based thing. That's yeah. I encourage you to look at the step response of the this fourth order system and see what the response you get and what you get it from the approximated system. You will be able to see that approximated system is good enough to start with for the PID control, because here your poles are like your time constants are 10 times away from each other. So it's 1.1, 0.01, and 0.001. So you will be able to nicely neglect the higher order terms and push a little bit of it into the model here. Yeah. Omega star is your operating frequency. So you will consider um, uh, operating frequency means by which your reference signal is changing, right? So this reference signal is changing. You'll have some kind of an estimate saying that this um, um, reference signal is changing by at max this much frequency. So that limits your operating frequency. L is less than, Sudarshan is asking, L is less than 0.38 T. This condition is not understood. Um, in what context it was? It was again in the context of uh, the delays. If I'm not missing out, it is based on whether the PID control is going to be easy or difficult. You can correct me on that. Now, the you can see that the time constant of the system, right? Say, for example, time constant of the system is 1 second, all right? And your delay is 0.38 of it. Okay. So 0.38 to certain extent is coming from the exponential calculations and whatnot of the time constant, T by T and so on. But what you can consider here is since you are modifying your um, for try understanding it from a very simplistic way. If it's a first order system with a single time constant of 1 second, what will happen to the step response of the system? This will asymptotical, this will delay by 0.38 seconds. It's a first order time delay system, and delay is, say, less than 0.38 of the time constant. So by the time you are reaching to the time constant, you are some percentage of the final value, but delayed by 0.38 seconds. All right. So now when I'm modifying it with proportional control or the proportional plus integral control, this time constant is going to be modified and going to be lesser. Our objective will be like making it the settling time to be smaller than the original signal or the open loop system. Uh, so in that case, I will be able to um, modify it between 0.38 to the time constant of the system, right? But if it is more than 0.38, then this modification will not have a big difference, right? And that's the reason with a higher delay of the system with higher delays is difficult to control with PI. That's what the intuitive idea I can provide. Always try thinking from the simplified form of the system, whether it's first order system's response or the second order response. We've seen that first order system, asymptotic step response. That's it. Okay, you'll be able to analyze your queries over here. Sudarshan, does it give you answer? Thank you. Okay. If there are no more questions, Bharati ma'am, can we um, sign off then? And if there is a requirement for another session, I am always available. We'll wait for 2 more minutes before ending this session. Sure. Thank you. Okay. All right. Thank you for your queries, and I look forward for more queries if you want another session for it. Hope you'll enjoy this. There was one more query. Oh, wow, wow. Okay. Does the PID controller used in industry auto tuning works as ZN method? In the older versions, yes, and ZN tuning is still the popular one. Cohen Kuhn is another popular one, as I mentioned. Um, Depending upon what the objective control objective is being said, right? We have already said what is ZN tuning objective is and what is Cohen Kuhn or other methods are. Process industry is very much using ZN tuning till date, and auto tuning is based on ZN tuning. How phase shift decides the system dynamics. Phase shift decides the system dynamics. It's like you have the phase margins available. If you go back and look at the Bode plot, for example, I will associate, I hope these are the, we have understood that these stability uh, tools that we have understood in terms of Routh-Hurwitz or the Bode plot or the Nyquist plot or any other stability way of finding the stability of the system. Some or the other way, they give us the idea whether the system, how much we have the idea of doing the stability margins available and so on. So in this case, I will take the example of Bode. All right, I'll use the tool Bode plot. Now, in the Bode plot, we consider phase margin, we consider magnitude margins. So phase shift is related to my phase margin available. If the phase shift is crossing that 180-degree point, then what will happen? If I am increasing the magnitude, if I'm having the you have a negative feedback system, right? If there is a phase shift more than 180-degree, then what will happen? The system will become positive feedback. Now, this positive feedback for those frequencies, system is turning into a positive feedback because you have a phase shift more than 180 degrees, so your signs are changing to negative here in the feedback channel. So that's where your stability constraints, stability issues are not being satisfied, and that's where the phase shifts are important to consider while doing the stability analysis. Yes, Namindu? Okay, to Sudarshan's question on the ZN tuning method, ZN tuning method or any such tuning method, it provides the baseline to start with the tuning. Because our models are not very perfectly designed available, the one that we do it on theory, the actual systems have small variations available. We always have to go back in the field and the tune the KPKI and PID controls, gains and so on. But these tuning rules gives you the baselines to start with, right? And then you look into the phase, the if I'm increasing the proportional gain, what is the how is it changing? How the Nyquist plot is changing, or magnitudes are changing at the output and so on. That is something you can consider. right? So that becomes a little bit of trial and error that time. But at least you have a baseline to start with. We will wait for another 2 minutes for any other question. So it's 11:48. I'll wait for till 50. All right. Thank you all for your queries and look forward for you to enjoy the course contents. Thank you so much.